Let's say you're a cell. And as a cell, you interact with the world through your surface. If you want to eat any food, it's got to come into contact with your surface. If you want any information about your environment, that information has to come through your surface membrane. Your surface is your connection to the outside world. It's how you interact with your environment. So as a cell, what you're going to want to do is maximize the size of your surface area, maximize how much area your surface occupies. So maximize surface area. This is one of your overall goals. So how could you accomplish that task? Well, one way might be to stretch yourself out, to contort yourself, to create some interesting shapes. Some cells have villi, which are projections which come off the surface and increase surface area. Some things like amoeba have pseudopodia, which are big stretchy arms that kind of come out, and these increase surface area as well. These types of structures might allow you to spread yourself out a lot further than you otherwise might have been able to. So if there's, for example, a little bit of food over here in your environment, maybe now you'll be able to grab that food and before you would not have been able to. So you can certainly see the advantage of having these pseudopodia or maybe having villi if you're an intestinal cell and how that would increase your interaction with your environment. But as you can also see here, in addition to increasing the cell surface area, I've made it a lot bigger at the same time. I've increased its volume. And one of the disadvantages of increasing volume is the cell is just bigger. It requires more food now. Bigger cells require more food. If I have any molecules that are entering the cell, they have a much larger space to diffuse into, so it takes longer for certain processes to occur. Larger cells are harder to maintain. So the overall goal for cells is going to be to maximize surface area, yeah, but also to minimize volume. They want their volume to be as small as possible and their surface area to be as large as possible. So is there a way that they could accomplish both of those goals simultaneously? And it turns out they can if they just make themselves very, very small. And it turns out this is the reason why so many cells are microscopically tiny in the first place, because making yourself small maximizes your surface area while at the same time minimizing your volume. The easiest way to visualize surface area to volume relationships is to imagine a cube and then try to understand what would happen to that cube as you cut it into smaller pieces. So here I will draw a cube which measures 2 by 2 by 2. If we wanted to calculate the area of just one face of this cube, it's pretty easy. 2 times 2 equals 4, so the area of a single face is 4. Now a cube has 6 sides, so to get the total surface area of this cube, you would just multiply that value 4 by the total number of sides, 6, in order to find that this cube has a total surface area of 24 square units. Now, in order to get the volume, you just multiply the length, width, and height together, so 2 times 2 times 2 gets you 8 cubic units. Simple enough. Surface area of 24 and a volume of 8. Now, if we slice this cube into different bits, we can cut it in half, and in half again, and in half again, giving us 8 cubes, which collectively have the same volume as the first cube, even though they are individually smaller. Now, let's calculate what their surface area and volume, total volume, would end up being. Assuming we cut each cube in half on the height, width, and length line, then that means that each of these smaller cubes is going to be 1 by 1 by 1, which makes all of these calculations very, very easy. The surface area of a single face of each cube is going to be 1 by 1, which means it's 1 square unit. And the surface area of each cube is going to be 1 square unit times 6 faces, so they will have a total surface area of 6, and they will have a total volume of 1. However, even though each one has a volume of just 1 cubic unit, there are 8 of these in total, because we cut it in half once, and then again, and then again. So collectively, 1 plus 1 plus 1 plus 1 plus 1, over and over again, for 8 times, we get 8 total volume. So these cubes collectively have the same volume as that first cube. What about their surface area though? Well, each cube has a surface area of 6 square units, and there are 8 of them, so 6 square units of surface area times 8 cubes actually gives us 48 square units of total surface area, which is twice the amount of surface area as the first cube. So just cutting up this cube into smaller pieces has increased the surface area without decreasing the volume whatsoever. Therefore, the surface area to volume ratio has increased. Now, I feel like this explanation is okay, but it would appeal to people who are somewhat mathematically and visually inclined, who perhaps already didn't need a great deal of help understanding surface area to volume relationships. So I thought I'd set myself a challenge of trying to explain this idea without using so much math, just an entirely visual or intuitive way of putting it forward. So if you understand the concept perfectly well, you are good to go on this video. If you still feel like you're struggling a little bit with it, stand by, I'm about to get a little bit messy. I'm going to need 2 model cells, so I'm going to need some Play-Doh to stand in for me. I have green Play-Doh, which will represent my large cell, and some yellow Play-Doh, which is going to represent my small cells. Step 1, of course, is to get the Play-Doh out of the jars, which proved to be the most difficult part of this process, but I did eventually persevere. Then I shaped it into 2 roughly cuboid-shaped cells, and made sure to measure them so that they occupied the same volume and surface area. Now, the volume is the amount of space that they take up. We measure volume in terms of, say, liters or gallons, right? How much space you could put inside of something, and we talk about cells in similar terms. The surface area is the 2-dimensional space that covers something, right? So it's the exterior portion of that thing. Now here I'm taking lots of measurements to make sure that they have the same surface area and volume. Unfortunately, I didn't realize that the measurements that I was writing down were out of the shot, so just take my word for it. These are roughly the same volume and surface area in shape. Now it's going to get a little bit messy, so I'm going to need some brown paper to not mess up my surface. And here's what we're going to do. I've taken all my measurements, and I know that the green volume is equal to the yellow volume, and the green surface area is equal to the yellow surface area. Now, what is surface area again? Well, if I have some paint, I can actually paint the surface area because the surface has an area. The area that I'm able to paint is the surface area, right? The more surface area there is, the more paint will be required to put on it. Bigger surface area, more paint required. Smaller surface area, less paint required. Since we know that both of these cells have the exact same surface area, we can assume that the same amount of paint would be required to paint the green cube as I'm taking up to paint the yellow cube. Now, what happens if we make the yellow cube smaller by cutting it in half? As you can see here, suddenly there is new surface exposed that wasn't painted before. All of the blue paint that we used before is still there. All of that same surface area from before still exists, but now there's new surface area exposed. Now there's new yellow to be painted in. So even though the volume is the same, we have all the same Play-Doh that we had before, the surface area has increased by simple virtue of the fact that we've decreased the size of the cells. Having more smaller cells increases the surface area even though we have the same volume. The total surface area of the 2 yellow cells is now greater than the surface area of the single large green cell because they are smaller. Okay, so I'll paint that new surface so it looks just like all of the others, but we could go even smaller. I can cut it in half again and expose even more surface area by creating even smaller cells. So now I have 4 yellow cells with an even higher amount of surface area than they have before, but the total volume is still the same as the single large green cell. I mean, you watch me take these lumps of Play-Doh from unopened containers at the beginning of the video, so you know that they have the exact same amount of material inside of them. If we call the green cube volume 4, it has 4 volume units inside of it, then we know that these yellow cells that have been cut into nice even little fourths must have each individually a volume of 1. So even though they have a smaller volume individually, added up together, they have the same volume as the original green cube there, but overall, a much higher surface area. So this is what I mean when I say that cells have to be small in order to maximize their surface area to volume ratio. You have a much higher amount of surface area relative to the same amount of volume if you have lots and lots and lots of tiny cells as opposed to one big giant cell.